Friends, up to this we discuss about the diffraction and also the interference. When we discuss about the diffraction at the time, we also discuss about that the diffraction has the limit on the resolving power of the instrument, optical instrument like as the telescope and microscope. Clear? So which type of the limit due to the diffraction take place in optical instrument? So today we are going to discuss about the resolving power of the optical instrument. First thing, what is the resolving power? Resolving power is that the ability of an instrument to produce the image of two closely objects. If the two objects are at the far distance are not shown clearly by our eye, at the time we are using the telescope. So how the image of these two close objects are formed by this telescope, that is known as the ability or the resolving power of this telescope. So here we are going to discuss about that. The resolving power of a telescope depends on what? Not only for the telescope, we also discuss for the microscope, because the telescope and microscope are two optical instruments generally we are using. So question is that, explain resolving power of an optical instrument, or explain resolving power of a telescope. Now listen, first, what is the problem? In optical instrument, due to diffraction, it is difficult to see the object and its images that are very close to each other. It means the two objects are at far distance and that is very close. So due to the phenomena of diffraction, we can't see these two objects separate or its images separately. So how this problem arises? For that purpose, the angular resolution of the telescope is determined by the objectives of the telescope. Already we learned about the telescope in chapter 9, ray optics. In telescope, it has the two convex lenses. One is object, second is the eyepiece. The diameter of the objective is less than the eyepiece in telescope. Therefore, the angular resolution of the telescope is determined by the objective of the telescope. That means the resolving power of a telescope depends on the objective, while the eyepiece only increases the magnification of the image obtained by the objective. What is the function of the eyepiece? Eyepiece is not resolve the image, but it only increases the magnification of the image produced by the objective. That means the eyepiece in a telescope acts as a magnifier, while the objective is used to increase the resolution of the images. That means the objective separates the image of the two close objects. Now, for that purpose, as you consider the objective is a convex lens and beam of parallel ray, or when a parallel beam of light incident on a convex lens. We consider the ray coming from the far object are almost parallel. Therefore, the parallel beam of light is incident on a convex lens. The ray must be focused at the principal focus of a convex lens. After the refraction, this beam is focused at a particular point, and this point is principal focus. But due to diffraction phenomena, the reflected ray beam will be focused in a finite region or the finite area instead of being focused at a particular point. Here, phenomena of diffraction take place due to that this ray or whatever the beam of parallel light is not focused at the principal focus, but there is a focus in finite area instead of particular point. So due to this convex lens, dark and bright fringes are obtained, but the dark and bright rings are obtained around the central bright ring. So when this reflected parallel beam is focused in a finite area, not focused at a particular point, but here the dark and bright, there is the bright, there is dark, bright, dark, bright. These type of rings are obtained around the central bright area. And these rings are known as S rings. That is known as the S ring. Okay. The radius of the central bright area. So this central bright area, actually there is our central maximum. In difflection pattern, we know that on the screen the difflection pattern are formed like this way. The central part is known as the central maxima, right? Either side of the central maxima we obtain the first minimum. After the first minima, first order secondary maxima are obtained. So corresponding to the central maxima, the central region is there. After that, there is the first minima. Due to the first minima, here the dark rings are obtained. Again, the bright rings are obtained due to the first secondary maximum. Now, the radius of the central maxima or the radius of central bright region is R0, and if F is the focal length, F is the focal length of a convex lens, and 2A is the diameter aperture of a lens, or the diameter of a lens. So in that case, the linear width of a central maximum, is 1.22 lambda upon 2A into F. Already in last lecture we discussed about that the linear width of a central maximum is equal to angular width into capital D. Capital D is the distance of the slit and screen. Here the distance between the lens and screen is F. So this part is the angular width, 1.22 lambda upon 2 into F. Therefore, radius of central maximum. So this distance is the width of a bright rings. Now the radius of a central maximum, that is our R0. That is our R0. R0 is equal to half of this linear width of a central maximum. Therefore, R0 is equal to 1.22 lambda F upon 2A. So it's equal to 0.61 lambda F upon. Already we know that from the figure, F into delta theta. So here there is suppose there is the delta theta. So in this right angle triangle, tan theta is equal to R0 upon F. Here the tan theta is equal to R0 upon F. But theta here is very small, therefore delta theta is equal to R0 upon F. Therefore R0 is equal to delta theta into F. Therefore F into delta theta is our R0. That means there is the radius of the bright ring. Is also same as 0.61 lambda F upon A. That is from figure. And therefore delta theta is equal to, there is the angular width, 0.61 lambda upon A implied. That must be, if the delta theta is this value, at that time we can see the image of the two close objects distinctly and also separately. Clear this thing? On the base of this, we are going to discuss about what is the resolving power and what is the resolution of a telescope. Clear this? Okay, now for a telescope, we derive the last equation, delta theta is equal to 0.61 lambda upon A. That is the angular resolution of the telescope. That is the angular resolution of a telescope. So for telescope, if the delta theta is this value or this angle required for to obtain the distinct and separate image of two close objects. So this is the requirement. Delta theta is equal to 0.61 lambda upon A. Lambda is the wavelength of the incident light. Generally we are using the white light, that means the chromatic light. And A is the half diameter of a lens. That means the radius. Okay. Delta theta is an angular resolution of a telescope. Now, the inverse of delta theta of an angular resolution, that is known as the resolving power or the geometric resolution of a telescope. So 1 upon delta theta, that is our resolving power, that is denoted as RP, is equal to 1 upon delta theta. Inverse of angular resolution, that is known as resolving power or the resolution energy, or that is also known as geometric resolution of a telescope. Thus, when the diameter of the object A is greater, delta theta is small. A is the diameter of the lens is small, so A is greater, so delta theta is small. And so that for a telescope, A is larger than power of resolution is also higher. Right? To increase the resolution power, or the power of the resolution of a telescope, we have to keep the A is larger, therefore the delta theta is small, therefore the resolution power of a telescope is increases, but the resolution power of a telescope is higher. So hence there is the resolution power or the RP of a telescope. So RP is equal to 1 upon delta theta, or RP is equal to A upon 0.61 lambda, or 2A upon 1.21 lambda. So from this equation we can write RP is equal to A upon 0.61 lambda, or 2A upon 1.21 lambda. Now, after the discussion about the resolving power of a telescope, now we define the resolving power and also we explain the resolving power of microscope. Now, what is the definition of resolving power? The ability of an optical instrument to produce distinctly and separate images of two closely placed objects is known as resolving power of a optical instrument, but that is known as the resolving power. Again, what is the definition? The ability of an optical instrument to produce distinctly separate images of two closely placed objects is known as resolving power. After that, we discuss the resolving power of a microscope. For a microscope, as shown in the figure, the image of a point-like object by the objective of a microscope is shown. Again, as shown in the figure, the image of a point-like object by the objective of a microscope. In microscope also here the two convex lenses. One lens towards the object, that is the objective, and towards the convex lens towards the eye is known as the eyepiece. Here the eyepiece is greater than in diameter than the objective. Okay, now the image of a point-like object by the objective of a microscope is shown in figure. Suppose the diameter of a objective is D, focal length is F, and object is placed greater than the distance of focal length F, and image is formed at distance V. Due to deflection, the angular width of a central maximum that is theta is equal to 1.22 lambda upon capital D. D is the diameter of a lens. Here that is given again, diameter of a lens is D, focal length is F, and object is placed greater than the F distance, that means the object distance is more than the focal length of a lens. The image is formed at distance D. Due to the deflection phenomena, here what's upon the angular diameter of the central maxima. Due to the deflection, here the image is not focused at a sharp point, but here the image is obtained in form of the circular rings. So in that case, the angular width of a central maxima is theta is equal to 1.22 lambda upon D. So there is the figure of the microscope. There is the object. Object is placed more than the F distance. That means the focal length of a lens. D is the diameter of a objective of microscope. So image of this object is formed at here. But here, instead of the image, due to the deflection phenomena, here the bright and dark rings are around the central bright rings. So there is the central maxima. Here the width, angular width of this central maxima is 1.22 lambda upon D. And linear width of a central maximum is the angular diameter, angular width into image distance. That means the V into theta, therefore 1.22 lambda upon D into, there is our angular width, and V is the distance of the image from the lens. There is the image is formed. Already we discussed about the linear and angular width. Okay. If images of the two point-like objects are at separation less than V theta, that means if the separation of the two images or the images of the two closely placed objects is less than V theta, at that time we not get the two separate images of the two objects, but the images are coincide with each other. That means we obtain the mixed image, mixed single object. So we feel that there is the image of the single object, not the images are separate. But actually there is the image of the two closely objects are superposed on each other. That means these images are mixed, and it is shown as a single object. If minimum distance for the two images of the point-like object is supposed to be dm, the two images are separated at minimum dm distance. At that time, dm is equal to 1.22 lambda upon d into v upon m. M is the magnification, V is the image distance, lambda is the wavelength of the chromatic light, and B is the diameter of a lens. Okay. Therefore, where the M is equal to magnification, image distance upon object distance, in figure the object is placed near the focal length and image is formed at distance V. Therefore, M is equal to V upon F. Therefore, V upon M is equal to F. So in this equation, we substitute the value of V upon M. Therefore, the minimum distance for the two images of the two point-like object dm is equal to 1.22 lambda upon d into f. That is equation number 3. Okay. Now from figure. Here the object is placed at distance d and diameter of the lens is d. Image object is placed at distance f and diameter of a lens is d. Therefore, there is the right angle triangle. Tan theta of this triangle, here tan beta, there is the d upon f. Tan beta is equal to d by 2 upon f. Because total diameter of a lens is d, the half is the d by 2. Therefore, tan beta is equal to d by 2 upon f. Therefore, d upon f is equal to 2 tan beta. We substitute in this equation here f upon d. Here we obtain the value d upon f. D upon F. Therefore, F upon D is equal to 1 upon 210 beta. Substitute in this equation, therefore dm is equal to 1.22 lambda upon 210 beta. Therefore dm is equal to 1.22 lambda upon 210 beta. But here the F is very small, that means the object is placed very close to the convex lens, that means more than the focal length of a convex lens. Therefore, beta angle is very small. If the beta is very small, so in that case we take the 10 beta is approximate sin beta. Therefore, equation 4 becomes dm is equal to 1.22 lambda upon 2 sin beta. Now, if the medium of refractive index n is placed between the object and objective, so this lens is objective lens. Objective lens. If we place the here medium, having the refractive index is eta. At that time what's happened? So the distance between the two images dm is equal to 1.22 lambda upon 2n sin beta. Again, if the medium of refractive index is n is placed between the object and objective, object is this, object is the convex lens. As we place the medium between these two, having the refractive index is n, at that time the distance between the two images of the two objects dm is 1.22 lambda upon 2n sin beta, where n sin beta is known as the numerical aperture. That is known as the numerical aperture. And 1 upon dm is known as the resolving power of a microscope. That means the reciprocal of this, the distance between the two images is known as the resolving power or the RP of a microscope. Now, if the refractive index n of a medium is increased, what's happened? The resolving power of the microscope also increases. Because the resolving power RP is equal to 1 upon dm. 1 upon dm. Therefore, 2n sin beta upon 1.22 lambda is the resolving power of a microscope. As the n refractive index of a medium is increased, already this medium is placed between the object and objective. If the medium becomes the more denser, so refractive index also increases. Therefore, what's happened? The resolving power is also increases of a microscope. That means to increase the resolving power of a microscope, we have to place the medium between the object and objective. And if the refractive index of a medium is increased, so what's happened? The resolving power of a microscope is also increased. Now, value of sin beta in this equation is not more than 1 because the maximum value of the sin function is 1. Therefore, the resolving power of a microscope is inversely proportional to the wavelength. Again, here the value of sin beta is not more than 1. Therefore, the resolving power of a microscope is inversely proportional to the wavelength of a light used. Therefore, the resolving power of a microscope depends on the wavelength of light used, and also if the medium placed between the object and objective, then it also depends on the refractive index of medium. If the refractive index of a medium is increases, so resolving power of a microscope is also increased. And if the wavelength of a light increases, so resolving power of a microscope is decreases.